Thank you very much. So, good morning. Today we'll be talking about multimodal robotics. Multimodal robots are robots that can display multiple modes of locomotion, which can be very interesting from a robotics perspective because they can move, for example, in the air, on land, underwater. Now, there are multiple examples of multimodal locomotion in nature, and I will show to you today how we can take inspiration in 3 cases from animals to design flying robots that can also display other modes of locomotion. Now, designing multimodal robots is very challenging, and the challenge is in minimizing the cost of transportation in the robot when it displays the different modes of locomotion. That's not a trivial thing to do, and I will show to you how we try to improve things over time. One of the very first examples of multimodal flying robots that we did was robots that can jump and glide. Now, jumping is quite interesting because you can have a small robot that can overcome very large obstacles. But the problem with that is that you can only perform small jumps and you have to do repeated jumps. And if you have wings that you can open or you can keep open, then you can prolong, you can extend your jumping trajectory and cover longer distances. And so one of the things, I'll be very brief on this, one of the things that we did was first to design a biomimetic jumping robot, which was shown a few years ago. And the main principle of this biomimetic flying robot is that just like small jumping insects, it loads energy very slowly on the legs, and it releases this energy very quickly on the ground so that it can perform high jumps. Now, one of the problems with these robots is that it's still very efficient, I think, in the sense that it can jump up to almost 30 times its height, and it can do on a size of 4 centimeters and approximately 10 grams, it can repeat 120 jumps. The problem is that after a jump, you need always to go there and upright it. So what about adding wings to this robot? It would not only prolong the flight, but it would also help the robot to fall on the ground with the legs touching the ground. And here you see the example of the robot. It loads the legs slowly, then it performs a jump, and the wings help the robot to land in the right position. It's not the best jumper we have seen on this planet because the wings are wide open, but it's already quite an interesting combination of the 2 modes. Okay, now we can combine wings with other modes of locomotions. For example, we may want to have robots that can fly and walk. Now, there are examples in nature of robots that can fly and walk. And of course, they can use their legs for walking, but one of the very interesting examples that I found is the bat. It's the vampire, actually, which can change its morphology to reuse the tips of the wings for performing steps or jumps, as you may want to call this. And this is quite interesting because you may imagine you have a flying robot with open wings that can cover very long distances, for example, 5 to 7 kilometers on a battery charge and back. And when it reaches the target destination, you may want to have this robot going down to the ground and do some exploration, some local exploration without flying. And that has 2 advantages. One, you save battery. Second, you may spend more time sensing and communicating in the environment. So a very simple way of approaching this problem is to take a flying platform, a fixed wing flying platform, very simple one like this, and try to think how we could modify the morphology of this flying wing so that it can use the tips of the wings for walking on the ground. Now, if you analyze the morphology of a fixed wing robot like this, you see that there are 3 important parameters that you can change that gives you different type of robots, as you see here on the right, which have different characteristics when it comes to walking on land. And these characteristics these parameters are this swept angle that you see here, the taper ratio, that is the ratio of the length of this segment and of this segment here, and then the inner ratio. The inner ratio is the distance between the center axis of the fixed wing and the point of rotation of the tip of the wings, so you can change this. So what we can do is that we can explore the morphological space of this robot, and we can measure the cost of transportation for this robot on the ground and try to find a compromise of the cost of transportation when the robot walks and the cost of transportation when the robot flies, because the different configurations have different costs. And so using this principle, we came up with optimal values. We did an exhaustive exploration. We came up with optimal values of these 3 parameters. And we have this robot that is capable of walking on the ground and also flying in the air. Now here you see the characteristics of the robot on the ground. It's not a very fast robot when it walks, but it's not so bad either. And when it flies, it's almost like a fixed-wing flying robot. It still has an autonomy of 30 minutes for a robot that is approximately 450 grams, which is not so bad. So you see here, we can launch it by hand. Here we have a robot that is used as a camera. So it does regular maneuvers, and once it lands on the ground, it can use the tip of the wings for performing locomotion, as you're going to see in a moment. So we had to do a number of things here, including the material that we put on the tip of the wing so that we can ensure there is sufficient grip. But as you can see, it can overcome quite large obstacles and also, for example, move on snow. However, there is a problem with this robot. And the problem is that the 2 modes of locomotion, flight and walking on the ground, are sort of incompatible when it comes to, for example, the torque and the rotational speed of the motors, or when it comes to where the center of mass of the robot is, because flying and locomotion require different positions for this. And a number of other things, for example, the distance between the edge of the wing and the center of mass of the robot. So what I came up with is what I call the principle of adaptive morphology. The principle of adaptive morphology means that is a morphological change that minimizes the cost of transportation in 2 or more incompatible locomotion modes. I already mentioned for you, in case of a flying robot that also displays other modes of locomotion, we have these 3 parameters that are incompatible. That means they need different values in the 2 locomotion modes. And this is what we want to do with the principle of adaptive morphology. We want to design systems that can change their morphology while minimizing the cost in these things. Now, animals like the bat that I've shown you before, but also birds, for example, they have articulations on the wings that allow them to maximize the benefit of these 3 parameters depending on what they are doing, whether they are walking, or whether they are grasping things, or whether they are flying. And what we came up with, and I will be very short here, is with a new modification, with a new type, a prototype of robot that is capable of folding its wings so that it minimizes the cost of transportation in the 2 locomotion modes. Here is a video of this robot. So you see here we have what we call the wingerons. These are the tip of the wings which are used for locomotion. And one of the things that we need to do now when we want to walk, we have to bring these wingerons closer to the center of mass of the robot. And for that, we use an articulated system, which is a replica, if you like, of the arm of the bats and the arms of the birds. So you can see here the wings retracting. And then we have a number of other things like gear reduction so that we can make the motor operating in the appropriate regime depending on the locomotion mode that the robot is displaying. And so with this type of design, now we have a robot that can fly very nicely. And when it's on the ground, it can also move by decreasing the cost of transportation with respect to the previous prototype. Now, for sake of time, I'll have to move on to the next topic. So these robots are quite nice. But if you want to fly out in the environment and then you want to reach an area where you want to do exploration, for example, an area like this one, this is a photograph from the Fukushima disaster, you will find that there is a lot of debris. Now, walking robots can overcome some of these obstacles, but other obstacles, like, for example, cables or poles like this, are very difficult for a robot to avoid. Now, the robot that I've shown to you before has some soft structure that can absorb impacts up to approximately 8.2 meters per second. But still, there would be some type of obstacles that would damage the robot. And so, some time ago, one of my students, Adrien Priot, went to visit Rob Wood's lab at Harvard, and he was filming insects colliding with walls. And one of the interesting things that really struck me was that insects use quite a lot the legs to not only to upright themselves when they are on the ground, but also to negotiate the way in which they hit obstacles and the way in which they move around. And so we decided to rethink how robots, flying robots, go and explore situations where there are a lot of obstacles around. And so we came up with this robot design. It's a hovering platform which has retractable legs, which normally when the robot is flying are retracted. And as the robot is on the ground, can be opened to upright the robot, for example. So here we have a prototype of this robot. You see it is protected by a cage. It is a cage that can absorb quite strong impacts. And what you see here is the leg, which has been closed and deployed in order to upright the robot. This robot has very simple sensing. It has a light sensor, and its goal in this particular case is to fly towards the light at the end of the corridor. So instead of having complicated sensors and complicated artificial intelligence, we have a morphology that can absorb collision, allows the robot to upright itself, and eventually get to the goal. So it's a very nice trade-off between intelligence and sensing and morphology, I would say. Now, the problem with this robot, however, is that as it moves around, it hits very often obstacles, and then it would fall on the ground. And this takes a lot of time. Now, we can describe the situation like this. We have a robot that is protected by a cage. And as the robot reaches an obstacle, hits an obstacle, then the cage will be tilted, and the propeller, which is inside the cage, will be tilted, most likely, which is not the same direction where the robot wants to go. And this increases the cost of transportation because it takes a long time just to get to the desired location, and also it takes a longer time to fly again down up from the ground. And so we came up with a different design where we have a robot now which is embedded within a gimbal structure. This is a passive gimbal. So as the robot flies and it encounters an obstacle with the outer cage, the outer frame will rotate around the inner frame, and the inner frame with the propeller will remain very stable, passively stable. And this reduces the cost of transportation because your robot can just slide against the wall. Now, once you have a robot like this, you can imagine that you can use it like a ball that rolls on the ground. So we have multiple modes of locomotion. We can decide to be in the air, or we can decide to reduce the power of the motors and simply let the robot roll on the ground and, for example, exploit hills, for example, going downhill. Now, using this design, we came up with a robot which I let this video describe.
The goal of this flying robot is to reproduce the amazing capabilities of insects, especially the fact that they can collide into things and continue flying afterwards. To reproduce this, we realized that we could put a lot of intelligence in the mechanics by having this rotating frame around the inner frame that always remains stable even when there are collisions. So this allows us to send the robot in very difficult environments, for example, for search and rescue missions, where there are lots of obstacles. And we can do that without complex obstacle avoidance techniques, so that we have a very lightweight platform. The novelty of this platform is its rotating protective frame. It decouples the inner frame with all the stabilization system and avionics, so that when a collision occurs, the inner frame remains stable and only the outer frame rotates. To test our robot, we flew it completely autonomously through a forest. We just gave it a magnetic direction, and without any obstacle avoidance technique, it was able to fly for several hundred meters while encountering multiple collisions with trees.
So you can see if you have a camera in the middle, it is automatically stable, it is passively stable.
Designing and building a flying platform like this is very challenging. The first challenge that I had to face with is the weight. That's why I built this robot with the carbon fiber materials. The second one is the balance, so the robot could remain stable after the collision.
The main advantages of this platform is that it is very robust and lightweight. And that's because it doesn't need heavy and complex sensors for obstacle avoidance. In fact, this robot can even use collisions and have the obstacle guide it. We think that this platform will allow rescuers to access places that no other robot can access. And we hope that one day we'll be able to achieve the amazing capabilities of insects.
So what you see here is another example of what I call this principle of adaptive morphology. You can either add actuators and motors to your robot and display multiple modes of locomotion, and that's okay. But then your cost of transportation will be quite high in all of these modes. Or you can change the morphology of the robot. You can either do it dynamically or change the way in which you conceive the robot so that you decrease the cost of transportation in both locomotion modes. And out of this, we have a very nice spin-off now. So as we release this robot, there has been a lot of interest in the inspection community, in the rescue community, and also in the defense community, because the robot can go into situations where there is a lot of structure, like, for example, under the bridge, where you've got truss or you've got cables, and you can use this robot for inspection. Okay, so this concludes my presentation. And I hope I showed to you how we can have our multimodal robots are a very interesting one, and how important it is to look at the morphology of these robots, and in particular at how we can change the morphology, how we can make this transition between the multiple locomotion mode. Before closing, I would like just to make a small advertising. I'm now hiring. I'm looking for 1 postdoc and 3 PhD students to continue investigation along these lines and also along the lines of new materials for soft, foldable robots that can display multiple modes of locomotion. Thank you for your attention. I expected a few minutes of introduction. That's why I timed for. The last one. At the moment, the autonomy is 7 minutes. In the product, which will come out next year, it will be increased. And also there will be an additional payload that can be taken on board. Okay, in the, yes, in the video that we have shown, in the paper, in the scientific paper, we put a magnetic compass and we simply let the robot go. And again, the concept here that what I really like is to trade the sophistication in the artificial intelligence and sensing with morphology. So instead of having a complicated sensor that can avoid the trees, we have a morphology that can absorb the collision, and all we need is simply a magnetic compass. We say, go north. In the product, we will have a remote operation because people want to be in control. And possibly we will have a video link so that you can always see with the camera within the inner frame where the robot is going. I think there is one more there. Yeah, it's a good question. So in the examples that we have, that I've shown here, it is not so important. Once you are, well, it's not true. I'm sorry, it's not true, because for the gimbal, it's very important that you can absorb the collision. And for example, if you want all of a sudden to roll on the ground, you don't want to have a mechanism that switches on the passive mode or switches it off. You want to be immediately able to move. So I would say it's application dependent. Oh, I didn't show, you're right, I didn't show that because I thought it was trivial, but it's because of I'm sorry, I should have shown that. You can imagine as it is on the ground, you simply move along a direction. You don't put so much torque on the propellers, you don't rotate them so quickly so they don't fly. You simply roll on the ground. And you can switch the propellers off. If you feel, for example, that the robot is moving with an IMU, you can feel the robot is going downhill, you can switch the propellers off and simply let it roll. Maybe we should put on some videos where the robot is also rolling. You're right, that's a good point. Okay. Thank you.
Hi, my name is Helen Kelasidi, and I'm PhD student at NTNU. In this presentation, we will show a model of. In this presentation, we will show a model of underwater snake robot moving in a vertical plane of 3D. Co-authors of this paper is my supervisors, Professor Christine Petersen and Professor Jan Tommy Grabach. General snake robots has been studied due to their ability to move in irregular environments. Now compare the amphibious snake robots to the ground snake robots. The former one has the ability to move over the land and swim in the water, while the physiology of the robot remains the same. So, in this paper, we propose a model of underwater snake robot moving in a vertical plane of 3D, which results in a closed form solution, avoiding the numerical evaluation of the drag effects, while considers also and models the hydrostatic forces. In particular, we derive the kinematics of underwater snake robot. We propose a hydrodynamic model which considers both the linear and nonlinear drag forces, the added mass effect, the fluid torques, and the current effects. And in addition, we model also the hydrostatic forces due to the buoyancy and the gravity. The equation of motion looks like shown here. And as I said already, there is a closed form solution, and they are particularly well suited for modern model-based control strategies. Some simulation results regarding this model for a lateral undulation motion shows that when we consider a hydrodynamic model, when we take into account only the added mass and nonlinear drag effects, we see that the small variation between the density of the robot and the density of the fluid affects significantly the overall motion of the robot. While in case that we consider a more detailed hydrodynamic model, the differences between the densities has neglectable results in the motion of the robot. This proposed modeling approach is valid for motion of an underwater snake robot in any 2D tilted plane of 3D under the assumption of a neutrally buoyant underwater snake robot, which means that an underwater robot moving in a horizontal plane falls out as a special case of the proposed modeling approach. Thank you very much for your attention.
Good morning, everybody. I would like to present my paper, Actuation Strategies for Underactuated Robotic Hands. My name is Mahmoud Tawakkuli, and I'm with the Institute of Systems and Robotics, University of Coimbra from Portugal. So while you are watching a short video from the ISR soft hand that will, by the way, will be presented tomorrow at the same time frame, just give you a short introduction. ISR soft hand is an anthropomorphic hand that contains 10 degrees of freedom that are compliant joints and 3 actuators. The actuators are used for flexion of the thumb, flexion of the index finger, and flexion of the rest of 3 fingers. The question that we encountered was that, is that the best actuation strategy that we can take, or there is a better one? So we looked at the literature. There are hands from 1 degree of freedom to 21 degree of freedom that contain 1 actuator to 5 actuators or 6 actuators. But the information about the actuation strategies of these hands is often missing in the literature. So in this study, we would like to answer this question: how the actuation strategy affects the functionality of the underactuated hands in terms of grasping. To do so, we developed 16 configurations with 1 actuator through 5 actuators. For instance, configuration 3.1 is a configuration that has 1 actuator for flexion of these 4 fingers, 1 actuator for flexion of the thumb, and 1 actuator for abduction and adduction of the thumb. Then we used a comprehensive grasp list that was developed by Thomas Fakes in 2009 to do this analysis. We defined some criteria, and we performed the analysis. Of course, in the interactive session, you will get more details about this. So we did 2 studies. In the first study, which is grasp diversity, we considered all 33 grasps. These are configurations, and this shows how good each configuration does in terms of functionality of grasping. And in the second one, we considered grasp functionality is a study that considers only the top 10 grasps, which are grasps that are highly used by human beings in the daily task. So as you can see, we can find out which of these configurations are doing better. So this table concludes, is summarizing the configuration against the score that they got in the grasp diversity and the score that they got in the grasp functionality that will be useful for the designers of the hand in order to find out how good their hand is doing and if they can optimize the design of the hand. For instance, as you can see, this is one of the best configurations that can do 22 out of 33 grasps with only 3 actuators and with 81.6% of grasp functionality. Thank you for your attention.
Okay, my name is Richard Primerano. I'm from Drexel University in Philadelphia, Pennsylvania. Today I'll be presenting some work that we've done toward the development of new rolling and crawling gates for snake-like robots. So if you're familiar with snake-like robots, a common kinematic structure is a series of rigid segments coupled through rotational degrees. These might be single degree of freedom rotational joints or 2-degree rotational joints. So what we're presenting here is a new coupling structure that provides 3 degrees of freedom per segment. And in addition to the traditional bending mode that you would get in a 1-DOF coupling, we also achieve what we call offset or lateral shifting and this extension contraction type of motion, which allows the robot to extend and contract like an accordion. And naturally, we can combine these modes into arbitrarily complex behaviors. So we've demonstrated a handful of gates on this robot, including some that you'll see in the literature, such as lateral rolling, linear progression, but we've also demonstrated a few new ones. Offset rolling, crawling, and dynamic rolling have been demonstrated on this robot. So this is best illustrated through a video. First, offset rolling. The robot's segments slide laterally and continually kind of push the robot in one direction. Lateral rolling is where the robot assumes a slight curve and then rolls its body about that curved axis. And again, you'll see this in the literature. This is a new gait for this robot, where the segments lift themselves up, move forward, and drop back down. And we call this head-to-tail crawling. We've also shown a few gaits in simulation that we have not yet tested on the real robot. Linear progression is a gait that you'll see on many snake-like robots. This creepy-looking one, this even-odd crawling one, is where segments alternately lift themselves up and then drop down. Lateral rolling, which we showed on the real robot a second ago, and we've showed a few other interesting gaits as well. This simulation shows a little more clearly how the offset rolling gait works. Segments continually slide with respect to one another and push the robot around. There are some interesting dynamic gaits. This robot is actually falling forward by lifting its segments up and shifting its center of mass in an appropriately timed sequence. So we can demonstrate a few interesting dynamic gaits as well. So right now what we're looking at is quantifying the energy consumption of these gaits. We're currently looking at these in simulation, but we've begun instrumenting the physical robot to look at things like the energy consumption as a function of how high I lift my segments or how much of an arc I take in one of the bending gaits to get an idea of how these gaits perform under different circumstances. So we've taken the simulation results and we've begun instrumenting the real robot with current sensing at each joint. We're looking at things like power consumption of gaits, the forward speed of the robot, and terrain handling ability, so we know which gate is optimal for which type of terrain. Thank you.
Hi. Today we'll be going through how the fastest micro-robotic fish was developed, our robotic fish, namely iSplash Micro. It's only 50 millimeters in length and can accurately generate the posterior kinematic pattern of the craniophone swimming mode at intensively high frequencies of 19 Hertz. This is a real-time video of the small fish during field trials, achieving maximum swimming speeds of real fish. measured in body lengths a second, with a consistent maximum velocity of 10.4 body lengths a second. In comparison, current robotic fish have achieved a maximum velocity of around 1 body length per second. Live cranioform fish, such as the common carp, cruise around 3 body lengths a second and have a maximum velocity of 10 body lengths a second. Our main objective was to develop a high-speed millimeter scale build, as miniaturization can greatly benefit underwater operations. The traditional approach of previous designs was typically confines the waveform to the posterior half of the body length. This approach creates interior destabilization for free-swimming robotic fish, therefore leading to kinematic errors over the full body length. Based on intensive observations of real fish, we introduced a full-scale body length approach for our first-generation prototype, which we found to coordinate the anterior mid-body and posterior parameters, increasing the linear swimming speed. 48 millimeters in height with vertical compression, similar morphological traits as real fish fins. This design of fin enables predictable optimization of the interior and posterior displacements. As we can see, mode 1, which has no fish fins, has a large anterior amplitude as predicted. Mode 2, with fins, greatly reduced the head amplitude. Mode 3, with fins, an increased tail amplitude compared to Mode 2 led to an increase in swimming speed. This approach allowed for a tail amplitude to be easily calculated by adjusting the offset crank. The developed mechanical system was found to be suitable for further reduction in scale. The low energy consumed during propulsion indicates the next generation may be capable of carrying a power supply. And the system was found to be robust and consistent, attaining high tail frequencies without early peak decline or mechanical failure. Therefore, we look to continue to raise driven frequencies to achieve even greater speeds. Thank you.
Hello, my name is Paul Lillebekk. I'm a postdoc researcher at the Norwegian University of Science and Technology. I will present a snake robot, which is waterproof and has a tactile sensor system. The purpose of this robot is to provide an experimental platform for investigating snake robot locomotion in challenging environments. And to this end, we have designed the robot so that it can both move on land and also swim in water. Mamba has a modular design, which allows different types of modules to be connected in different configurations. The modules we've developed so far include joint modules, head and tail modules, and different types of active propulsion modules. And some possible configurations of these modules are illustrated here. You can, for example, mount passive wheels on the joint modules, and we can attach legs or fins on these motorized active propulsion modules. The most novel feature of this robot is its ability to measure contact forces along the body from the environment. And this is achieved with a 6th degree of freedom force torque sensor installed inside each joint module. And the force sensor is based on strain gauges, and it measures the force and torque acting on each joint shaft of the robot. And all these joint shaft measurements can be mapped to the net external contact force on each module. We have experimentally validated the force sensor and found that it can fairly accurately measure forces and torques acting on the robot. And this was done with an experimental setup where we applied known forces and torques to a module and found the mapping from strain gauge measurements to these known forces and torques. We have also tested the swimming capabilities of this robot. Although each module of the robot is watertight, we have chosen to cover the robot with a protective skin to achieve an additional water barrier and also to improve or to reduce the drag forces along the body. Yeah. So thank you for your attention.
Good morning. My name is Dimitris Tsakiris, and I am with the Institute of Computer Science of Forth in Greece. I'm going to present a paper entitled Multi-Arm Robotic Swimming with Octopus-Inspired Compliant Web. And my co-authors are Michael Sfakiotakis, Asimina Kazakidi, Augusta Hadzidaki, and Theodora Demo. Our work is motivated by the outstanding locomotor capabilities of the octopus, one of the most intelligent and agile creatures in the sea. It has no rigid parts, and yet it is able to exert significant forces in its environment, so it is a paradigm useful for soft robotics. Several robotic systems have attempted to replicate some features of the octopus, primarily the manipulation of objects and its jet propulsion. In our work, we try to replicate a different swimming behavior, which is called arm swimming, where the arms are used for locomotion, as we see on the video in the left. Arm swimming is composed of a slow opening of the arms, followed by a rapid closing inwards, and this creates a burst of forward thrust, which the octopus exploits for hunting or escape. From an engineering viewpoint, we are interested in replicating arm swimming by a robotic system, as we see in the video on the right, because, first of all, it is fun. We go to test it in the sea in Crete. And also in order to develop multifunctional underwater robots where the same mechanical substrate could be used for both propulsion and object manipulation. We have developed computational models that account for body compliance and for the interaction with the aquatic environment. And we use them for studying the effect of motion parameters on the propulsion of the system. Also, we studied several patterns of coordination of the arms, as you see in the videos, which we call gates. And these computational studies assisted our design of robotic prototypes and predicted satisfactorily the characteristics of their behavior. The soft-bodied robotic prototypes that we developed are composed of 8 compliant arms and possibly a compliant membrane, which is called web between the arms. On the left, we see the morphology of the body parts. In the video, we see a race. At the bottom is a robot with relatively stiff polyurethane arms. In the middle, a robot with more flexible silicone arms. And at the top, a robot with both silicone arms and web. And it is clear who is winning. We also implemented behaviors like turning, crawling at the bottom of the tank, holding objects, and so on. Thank you for your attention.
Very good morning to all of you. I am Rohan Thakkar from the Vishveshwaraya National Institute of Technology, India. I am here to present a paper on the reconfigurable bipedal snake, which was done along with Ajinkya Kamath and Sachin Bharambe from the electronics department, and I'm from the mechanical department. This project was done as a part of our undergrad program under Professor K.M. Burchandi and Sheetal Chiddarwar. So this is basically a reconfigurable bipedal snake. So it's a snake robot that can walk. Now, why would you want to do this? So the advantage is that we get an alternate way for autonomous motion planning algorithms in snakes, and we get alternate gates which we can use to climb obstacles such as stairs, which are difficult in case of snake robots. So the design philosophy that we've used over here is we have a very simple design. As you can see, it's a modular architecture with a square cross-section, and the range of rotation of each joint is kept to 120 degrees. And the links can be fabricated using processes such as milling or laser cutting. The main principle that we are using is we are achieving reconfiguration without any rearrangement of modules, which is done. As you can see, these are a few popular reconfigurable robots. So the Rebus does not use any reconfiguration of the modules. So I have a video showing each of the following gates. This gate shows the transforming gate from the snake configuration into the walking configuration. And basically, it satisfies the stability criteria where the ground projection of the center of mass lies within the support polygon. And speciality about this configuration is that we are achieving walking without any lateral shifting of the center of mass, which is unintuitive when you think about walking. Oops. Jeez. I'll just play it from here. Yeah. So this is the walking gait where we don't have any lateral shifting of the center of mass. And that's the reconfiguration back into the snake gait. And it's in less than half a second. So this is the sidewinding motion which is there in traditional snakes, along with turning. And it can also roll. Thank you.
Good morning, my name is Gwang-Kyun Jung from Biorobotics Lab in Seoul National University. I'm going to talk about how compliant leg affects the jumping performance. This fully inspired jumping robot uses a torque reversal mechanism. First, it stores the energy at the SMA spring actuator, and when the trigger is activated, the direction of the torque is changed, and robot starts to jump. During the jumping, this robot goes through very high acceleration and it causes the leg to be bent. And this compliant leg can be seen in other types of jumping. The main difference is this very small-scale jumping robots, the amount of input energy is fixed, and the fast takeoff speed energy means that high energy efficiency. But in other jumps, in case of run-up, the input energy can be different depending on the run-up skills, and in periodic motions, the high takeoff velocity may not ensure system's stability. So the idea is that how much energy is really used for jumping out of the fixed amount of initially stored energy. So we employed the conversion efficiency that shows the losses during conversion of stored energy to kinetic energy, and is given as the ratio of converted energy to initially stored energy. And if we take a look at the instant of takeoff, where the vertical erection force is 0, interestingly, the robot takes off with its leg being bent. And this may seem very inefficient since the energy stored in the leg is consumed as a leg vibration. So to investigate how this leg stiffness affects the jumping performance, we prepared 5 different legs having different leg stiffness, and is switched out by using the chain memory polymer rivets. So here's the result. The first is the compliant leg shortens the takeoff time. This is because this compliant leg cannot perfectly support the high compression forces and the bending moment. As a result, the speed of mechanism, the operation speed of a mechanism gets faster. And the second, this graph shows the energy distribution at takeoff. The kinetic energy and the conversion efficiency is maximized in this case. And if we take a look at the residual energy, which is unconverted portion of initially stored energy, as you see, the optimal case converts more energy compared with the rigid cases. And this tells us that the robots can use the more portion of energy, although it consumes the energy as a leg vibration. Thank you.
Hello, my name is Christian Holden, and I'm here to present my latest work, Optimal Dynamic Force Mapping for Obstacle-Aided Locomotion in 2D snake robots. And I'm here on behalf of the Department of Engineering Cybernetics at the Norwegian University of Science and Technology in Norway. So first, a brief introduction to snake robot. You've basically seen this already since all my colleagues had basically the same slide. So snake robots are, let's see. Yeah, so snake robots are elongated, well, snake-like robots, and the reason we're interested in them is because they have abilities that few other robots have. The original concept at my university was a self-propelled fire hose, so the fireman was just supposed to be able to press a button on the fire engine and the fire hose would crawl into the burning building or whatever and put out the fire while the fireman could sit back and have a nice cup of coffee or something. They also have the ability to move in very confined areas, and they use the clutter in the environment to increase their mobility, unlike regular robots, which are hampered by excess clutter. They can also swim, and as this video shows, they have the ability to crawl both on the inside and outside of pipes, which is useful for inspection and maintenance. So the stuff I've been working on is obstacle-aided locomotion. So in this case, we have the green snake, which is here touching a certain number of obstacles, which are the circles. And if the snake uses some torque at the joints, then since it's pushing against the obstacles, you will get reaction forces, which are the red lines here. And this will, in sum, give some total force on the snake center of mass. So what we're asking is then, given a desired acceleration for the snake center of mass, which forces do we then need to generate to create these forces, and which torques should we use to generate these forces again? So in my paper, we present a new model of non-uniform snake robots in contact with obstacles. We find an optimal method of using motor torques to move the snake robot as desired, and we find a method to determine offline the quality of a proposed path for the snake robot, so that we have some way of figuring out if the user-chosen path is at all useful or not. So if any of this sounds interesting, please drop by and ask some questions in the interactive session later. Thank you.
My name's Apurva Kapadia. I'm with Clemson University, and I'm presenting closed-loop control experimental results of the controllers we've developed for extensible continuum robots. So what we're doing is we're presenting the experimental performance of 3 controllers for extensible continuum robots, specifically on the OCT-arm. So we have 2 configuration space controllers that we compare against each other. One is a proportional derivative controller, a standard one, adapted for the OCT-arm, and the other is a sliding mode controller. We also have one task space controller that we are presenting, whose results are shown here, and that is a simple feedback linearizing controller. While the controllers, at least mathematically, have been developed for the 3D motion of the OCT-arm, because the dynamic model that we have is only a planar 2-dimensional model, this work, the experiments that we show, are also restricted to that plane. So a basic definition of continuum robots, they are robots with continuous backbones, and they're inspired by elements of the animal kingdom, such as giraffe tongues, elephant trunks, squid tentacles, or octopus arms. So the point of these robots is that they can bend at any point along their structure. As opposed to rigid link robots, these robots can bend and therefore can pick up objects with weird shapes, and also navigate a little better than certain types of rigid link robots in unstructured environments. Now, there are various designs available based on this paradigm. We have a pneumatically inspired robot, and it's called the OCT-arm, which has 9 degrees of freedom. It has 3 serially connected sections, the base, the mid, and the tip, and it is based on McKibben actuators. And it's capable of 3D motion and is therefore redundant, and we have string encoders along the lens to measure the length and curvature of every section. The overview is we have this basic block diagram. Our controllers are based on the Lagrangian model. We track trajectories, simple error-based controllers. We have 3 results. The results are generally pretty good. This is for the PD controller, for the sliding mode controller over here, and for the feedback linearizing controller. I have videos also to show at the interactive session if anyone is interested. In general, the tracking results were very good, although they cannot necessarily be compared to those of rigid link robots, because the accuracy of the tip or the sections does not have to be as high. It's the general shape that we are keeping in mind. So that's something to consider when we look at the performance of our controllers. The video results are available at the interactive session again. And I welcome any questions at that point of time. Thank you.
Good morning, everyone. I'm Vasu Raman. I'm from the California Institute of Technology, bringing about a little bit of a topic change. I'm going to be talking about my work on reactive switching protocols for multi-robot high-level tasks. So in this work, we're going to concern ourselves with teams of cooperative, homogeneous robots operating in non-deterministic environments. We're also going to assume that we have a task specification that's been provided to us in linear temporal logic, or LTL, and more specifically the GR1 fragment, for those of you who are experts at LTL. And finally, I'm going to assume that the specific assignment of tasks to robots is unimportant as long as all the tasks get done. So some motivating applications in this domain include robots operating in a warehouse in the presence of humans and other non-deterministic elements, and robots operating in a disaster response setting, among many, many others. The way I'm going to solve this problem is to model the robot team as a switched system in which the mode corresponds to the specific task assignment to each robot. I'm then going to construct motion controllers for each mode that drive the team of robots to a goal configuration specific to that mode. And there are several ways of doing this in the existing literature, among which include approaches that partition the joint configuration space into polytopes and find local feedback laws to drive between adjacent cells. I can talk about this more in the interactive session if you come see me. And finally, what I'm going to do is synthesize using a provably correct formal synthesis algorithm, synthesize a switching protocol automatically that yields a switching policy such that the resulting controller provably satisfies my specification fee, even in adversarial environments. The key contributions of this work include a novel approach to concurrent task assignment and planning via reactive synthesis, an exponential improvement in computation, which results from the switched system representation over existing approaches. And finally, by making this explicit separation between the motion controllers and the robots, we're introducing a level of virtualization that lets us solve otherwise infeasible tasks. So in the simulation, you'll see 4 robots patrolling a workspace. There are some marked areas that they're supposed to visit, and you'll see them kind of switching goals in response to the appearance, the closing and opening of non-deterministic doors. And if you want to hear more about this and other examples and discuss the work a little bit more, please come to the interactive session, and I'd be happy to discuss it with you in detail. Thank you.
Hi. In this work, we introduced and solved an informative path planning problem called the correlated orienteering problem. Now, our goal is to enable one or multiple mobile sensing robots with limited travel range to optimally collect information over a network of spatially distributed and correlated nodes. In the classic orienteering problem, there are some rewards, in this case, these treasure chests that are scattered at various locations. Now, there may be one or multiple treasure hunters who want to collect those rewards. Often, they are limited by how far they can travel. For example, in the case of a pirate, the pirate ship might only have limited food supply that lasts a few days or weeks over the sea. Therefore, these treasure hunters, they want to plan very carefully a route so as to maximize the collected reward, while at the same time not running over its travel budget. Now, I want to mention that the orienteering problem and the problem we're going to introduce, they are all NP-hard problems. Now, the reward in the orienteering problem can be some form of information that we want to collect. Now, often, information at nearby locations, they are correlated. That is, the locations might form a network of nodes such that a mobile sensor visits and collects information at one particular node. That information will allow us to actually have some partial information about nearby locations. Now, with this setup, and assuming that these robots have limited travel range, we want to plan tools for this robot so that these tools respect the travel distance limit. And at the same time, the nodes visited by these tools, if we collect information over this set of nodes, we hope to best estimate through correlation the desired information across the entire network of nodes. Now, for this problem, we provide a mixed integer quadratic programming-based algorithm for solving a version of the correlated orienteering problem with a quadratic cost function. Now, I want to mention that this algorithm is complete. It's optimal. It extends to multiple robots in a very straightforward manner. The algorithm is also an anytime algorithm, meaning that it can compute a very good quality solution fairly quickly, and over time, gradually converges to the optimal solution. Now, for more computational examples and other details, please come to my interactive presentation. Thank you.
With the local perception of the ground of the UGVs. The problems that we want to solve are the relative localization, because basically we assume that the UGVs are identical to each other, and then also to control the entire formation. What we need to accomplish this task basically are, for the UAV, is an inertial navigation system, a sonar, and a camera, while for the UGVs are just an odometer and a proximity sensor for the obstacle avoidance task that we will see together. Basically, our algorithm is made up by 2 steps. The first one is a relative localization system that basically solves the add-on data association problem between the camera observations and the UGV's identities. And then the multitask control that is made up by 2 different tasks, so the primary task and additional task. The primary task consists basically in control the centroid and variance of the UGVs in the camera field of view, so in the camera image plane, so that the UGVs will remain in the field of view of the camera, and then the additional tasks that are the formation control, so to place the ground robot in a given position in the world, the navigation, move the entire formation along a given direction, and obstacle avoidance to avoid the obstacle on the ground. In the piece of the video that I want to show now, basically at the beginning the ground robots will move in a random way to favor the localization system, so to recover the identity of the UGVs. When the convergence is enabled, basically we move toward a given direction, but an obstacle appears. So thanks to the obstacle avoidance term, they will avoid the obstacle while the UGVs take care about the primary task. And also if there are multiple obstacles, obviously our algorithm is able to overcome these and to accomplish all the tasks. When the obstacle avoidance is neglected, because basically the obstacle is overcome, our system recovers all the tasks, and so all the execution are accomplished in a good way. Now, if you're interested in one of these topics, so heterogeneous system, multitask control, relative localization, or visual servoing, please visit us in our interactive section. Thank you.
The title of this work is Three-Dimensional Multi-Robot Formation Control for Target Enclosing. The authors are Miguel Aranda, Gonzalo López Nicolás, Carlos Agüez, Michael Zablanos. We are from the University of Zaragoza, Spain, and Duke University from USA. So, the goal of this work is to define a method for target enclosing of a multi-robot system. The contributions are that this method is for any 3D general pattern formation, and we are not using a global reference system. To formulate this problem, we propose to use to define a cost function, gamma, and given that we are not using a global reference, we need to define a rotation matrix, which is locally computed by each robot by minimizing this cost function gamma. To define the control law, we propose a method which is based on minimizing the cost function by using the negative gradient of the cost function. We show that this control law is exponentially stable. And these are several examples of this method. We can see different numbers of robots and different pattern configurations. We also saw that this method can be used if the target is moving, if it is a dynamic target. And we also finally saw that we can allow the formation to rotate around the target depending on the possible applications. So thank you.
Good morning. My name is David Portugal, and I'm going to present a work on multi-robot patrolling, which is the result of a collaboration between the University of Coimbra in Portugal and the Georgia Institute of Technology in the US. So we addressed the patrolling problem, which is literally the activity of going through an area in regular intervals for security purposes. And we intend to do this using a team of cooperative mobile robots in order to patrol the environment as effectively as possible. The patrolling problem finds application in surveillance, waste cleaning and monitoring, computer systems, defense and civilian applications. Using robots in these scenarios is advantageous since they have the ability to safeguard human lives. So we'll have the assumption of a topological map, which is extracted from a metric representation and is represented using a graph. So then our problem becomes to coordinate the robots in order to visit all the vertices of the graph while minimizing the idleness. This has been shown in the literature to be a NP-hard problem. So we propose to compare a total of 4 methods, 2 of them with non-performance bounds and 2 of them heuristics. These are all based on classical graph theory concepts like graph partitioning and TSP tours, which have been shown in the past to obtain near optimal performance. We then analyze the trade-off in performance, traveling costs, and the importance of coordination in multi-robot patrolling strategies. In this paper, we also provide the theoretical analysis and examine the patrolling routes generated by each different strategy across multiple environments. Our main results show that partitioning is generally suitable for large teams of robots and unbalanced graphs, while in the remaining situations, cyclic strategies are generally superior. An important result that we have obtained is that choosing a proper patrolling strategy depends not only on the topology of the environment, but also on the number of robots that we have available. In addition, graph partitioning is shown to promote team coordination and is more resource efficient because each robot patrols a disjoint subgraph, while in the cyclic approaches, all the robots share the same graph. Our heuristics have generated superior effective patrolling routes than the methods with non-performance bounds. And all our methods are freely available for the community to test with different graph instances. So this is it. Thank you for your attention, and I hope to see you in the interactive session.
Good morning. My name is Flavio Cabrera. I'm with the Engineering and Technology Department at Von College in the city of New York. Today I'm going to talk about the work I've done with my colleague, Professor Jishun Shao, from the City College of New York. The primary interest of our work is in quantifying the performance of multi-robot systems, particularly in the work we are doing today, one presented today. We're interested in the fleet size of multi-robot system, how increasing the number of robots is going to affect the execution time of any given task. For us, the task at hand is the exploration of structured environments, where structured environments are environments that constrain the movement of the robots, pretty much like indoor office-like, pretty much like these environments. Some examples you see over there. The discussion came about because there is this empirical assumption that more robots is going to help or is going to improve, is going to do any task that you assign to them to do faster. So the questions would be, when we were doing this work, we came up with these questions. We said, well, how much faster is going to be? What is going to be the ratio of improvement of increasing the number of robots? If we increase the number of robots, what will be the time, the value at which the exploration time or the execution time is going to converge, because there's going to be a limit upon which adding more robots is not going to improve the execution time. Actually, it might actually getting worse. So is there a limit in number of in the fleet size? Could be possible to delimit the fleet size by knowing if we know the size of the environment? So all these questions we had at the time. We decided to, we found out there are not too many, there are many different algorithms, but most of them are not being analyzed in a theoretical way, more like in a heuristical way. The result of our, I'm just going to show you the results. We have two results. The two results are two expressions. This one is for the exploration time of an structural environment, given the size of the environment and the number of robots being used to do it. And finally, this is like a bound, the maximum number of robots that, given an environment of a given size, are going to be needed. More details in the interactive session. Thank you.
Hello, I am Patricio Cruz. I am going to present today the work that we have done at the University of New Mexico about the stable formation of group of robots via synchronization. The coordination of multi-robots is required for different tasks like disaster relief operations. One of the challenges when we are working with this type of networks is to maintain a reliable wireless connectivity among the robots, among the robotic platforms. So far, RF has been used for the communication purposes, but this has some limitations, like, for example, some security issues, and also can have an unwanted interference in sensitive environments. So one possible application or technology in order to overcome this limitation is to complement RF with optical wireless communications, since it gives the advantages of larger bandwidth and also can give us an extra level of security. One recent application, for example, is the NASA that sends video from the space station using light. So our purpose is to create a direct line of sight link between an aerial vehicle and a ground vehicle. However, this is challenging because of the mobility of the user. So in this work, we pursue to solve the problem of a stable formation of a group of aerial vehicles with a group of ground vehicles such that we facilitate the line of sight between them. We apply synchronization to solve this problem. When we work with oscillators, they are generally characterized by this phase and its natural frequency. A common model for the N oscillator is given here, and we are in particular interested in a solution to this problem that is called an splay states. Essentially, this is saying that the agents around can achieve a circular formation in such a way that the faces are equally distant around the unit circle. So we we plan to apply this, as you can see here, in a way that we can achieve this final formation such that they are in a circular formation, also obtain the play state, and finally they are aligned in phase. We have added this extra term to the current research that has been done in this type of applications. So we have tested our control law in simulation and also with a real platform at the Mares Lab at the University of New Mexico. And as you can see here on the video, the vehicles, each group, the group of aerial vehicles and the group of ground vehicles that are working in different planes, they attain to, at the end, get this circular formation, as you are going to see, with display state, and at the same time to be aligned the one plane with the other plane so we can achieve our goal, that is to send communication. Thank you.
Hi, I'm Patrick McAlpine from the University of Texas at Austin. Today I'll be talking about some experiments in ad hoc teamwork research, which were held across a series of drop-in player challenges, also known as pickup soccer games, at RoboCup 2013, which is an international robotics competition where robots play soccer. So to begin with, and as an example to motivate the importance of ad hoc teamwork, suppose we have a natural disaster, such as an earthquake, where we want to send in a robot to help with the rescue and recovery effort. Now, at the same time, there might be some other organizations sending in their own robots to help out. We don't know who these robots are beforehand. We also don't know what their capabilities are. There is no chance for pre-coordination. However, we want our robot to be able to work with these other robots and adapt to them so that we're able to maximize performance of the overall team of robots for the task at hand. Ad hoc teamwork is where we have a team with some shared goals. However, we're not in control of all the agents on a team, and in fact, we often don't know who our teammates are beforehand. There is no pre-coordination. An example of this in humans would be pickup soccer. So the research question that we ask is, how can an agent cooperate with unknown teammates? Now at RoboCup, we held a series of pickup soccer games between teams consisting of randomly different chosen players from participants in the competition. We had international teams actually create agents specifically for this competition. Now there's no pre-coordination between teammates. Before a game, you don't know who your teammates or opponents are. However, we did provide teams with a standard communication protocol to help them actually work together while playing games. Now these drop-in player games, or pickup soccer games, were held across 3 different leagues at RoboCup, which now I'm briefly going to describe, as well as show quick video clips of actual drop-in player games. The first of these is the standard platform league, where we have Aldebaran Now robots. These are teams of 5 versus 5 autonomous robots playing soccer against each other, and they're able to communicate over Wi-Fi. Next, we have the 2D simulation league, and this is where we have agents using primitives such as dash, kick, and turn to interact with the environment and play soccer. And finally, we have the 3D simulation league. This consists of simulated robots modeled after the Aldebaran Now robot playing soccer against each other. And this simulator uses the Open Dynamics engine in order to have realistic physics. Now, some topics covered in our paper include how to create a testbed for ad hoc teamwork, how to select and assign agents to different teams, how to measure the performance of individual agents within an ad hoc teamwork setting, as well as some potential strategies for ad hoc teamwork. So if you'd like more information, you can go to the following URL, and also please come talk to me at the interactive session afterwards. Thank you.
Hi, everyone. I'm Sasank Nagavali, and I'm going to be presenting some work done at the Robotics Institute at Carnegie Mellon University on aligning coordinate frames in multi-robot systems with relative sensing information. This work was done in collaboration with Andrew Leibarger, Lindsay Lau, Nilanjan Chakrabarty, and my advisor, Katya Sakara. So there's many applications that require a multi-robot team and all the robots on that team to establish a common reference frame for operation. Basically, these sets of applications can be split into what we call the global localization problem and the coordinate frame alignment problem. In the global localization problem, you need to maintain a consistent reference frame over a long period of time for applications such as mapping, whereas for the coordinate frame alignment problem, you only need to establish common reference frame at particular points in time for exchanging information between your robots so that they can collaborate. And most importantly, the history of motion is not important. So we've developed some algorithms, both centralized and an asynchronous distributed algorithm, that use the inter-robot relative position measurements to actually extract the pose, which includes both the position and the orientation of every robot in the system in a common reference frame. The multi-robot system in our case must have an undirected sensing graph, and the communication graph must be the same as sensing graph, which means that two robots that can, if robot A can sense robot B must also be able to sense robot A. But we can prove that our algorithms are globally optimal, and they will converge if, to the globally optimal solution if the measurements are noiseless, or if the measurements are noisy and the sensing graph has a tree structure, which lots of other algorithms in the existing, most other algorithms in the existing literature can't prove. Otherwise, our algorithms are still locally optimal. So in systems with sensing noise, which includes all real systems, our distributed algorithm, which with the error refinement, will actually outperform standard methods such as Gauss-Newton and Leavenworth-Marquardt. On the far left, you'll see the how the Gauss-Newton algorithm performs, and that's the value of the objective function over several trials. And on the far right, you'll see how our distributed algorithm performs with error refinement, and you'll see that it's much better. So the Gauss-Newton was done in a centralized way. We've also verified our algorithms on real robots in an experimental setup. So this is one example of our experimental setup. Our undirected sensing graph is shown on the left, and the actual turtle bots are shown on the right. And the measurements are extracted from the depth information in a Connect. Each robot is identified by the QR codes on the robots. Our experimental results, I won't go through them in detail, but you can come visit me at the interactive session. As you can see, the measurement error, we don't make any assumptions on the sensor noise model, and we still get good results. Our future work will be on where the communication graph and sensing graph are different. Thank you very much.
Hello, my name is Alessandro Giusti, and I am presenting this paper on behalf of the authors, who are colleagues of mine and had a last-minute problem. We are all at the Dalle Molle Institute for Artificial Intelligence in Lugano, Switzerland. So we consider the problem of planning collaborative missions to be carried out by heterogeneous teams, which may include robots with different characteristics, or a combination of robots, humans, and even animal agents, such as rescue dogs. The key point here is that every agent has a specific set of skills and possibly different controllability. Our plans need to properly account for this fact and exploit the possible synergies among different agents. Heterogeneous teams can be successfully employed in various fields, such as cleaning, farming, and others. From the modeling point of view, we can see all these problems as naturally decomposable in a set of parallel, spatially distributed tasks which may require different skills. In our model, every task has an expected workload that can be incrementally serviced by one or more agents at different times. Tasks are therefore non-atomic. This is illustrated in the figure for the case of a cleaning task. Depending on their skills, different agents have different expected performance when dealing with the different tasks. The figure shows a simple example of a bad and good use of agents' skills for task assignment. Our goal is to design a planner that assigns tasks to agents and determines who does what, when, where, and for how long. This amounts to solving a multi-agent path routing and service scheduling problem. The planner can enforce specific proximity constraints, for example, to ensure that a human rescuer won't be sent in an isolated area without network coverage by flying robots. Plans are also computed to be robust to deviations in plan execution, which is, for instance, the case for partially controllable agents, such as rescue dogs, or because of unforeseen obstacles or malfunctions. We mathematically model the problem as a mixed integer linear programming problem which is solved with formal guarantees of optimality bounds using a standard solver. For computational efficiency, a meta-heuristic is used in combination with the solver to improve its anytime behavior. We study the application to search and rescue scenarios and empirically validate different aspects of the model. Thank you for your attention.